I thought I would do a series of videos that ultimately lead to a discussion of a really famous problem in theoretical computer science that's known as the P versus NP problem. And this is a fascinating problem, and I think one where much of the intuition can be accessible to a fairly broad audience. Now, over the course of the videos, I will be a bit fast and loose in terms of the mathematical rigor, but I'm going to try to make the topic much more intuitive, and if I try to make it too mathematically rigorous, then I think I'll lose some of the intuition in the process. Now, this particular problem, this P versus NP problem, some might even argue that it's one of the most important problems in the world, let alone in areas like mathematics. And I think what makes this particular problem so fascinating is that it really lies at this intersection between computer science and mathematics. Okay, and really the P versus NP problem combines elements of computer science and mathematics in its description and in approaches to try to solve it. I think it also has other broader implications. For example, you can even argue that it has deeper philosophical implications as well. Okay, now I want to point out also this particular problem, this P versus NP problem, is currently it's an open problem. And by open problem, it means that nobody has actually solved it yet. Now, it turns out if you do solve this problem, if you happen to come up with a clever way to approach this particular problem, not only will it be a major mathematical breakthrough, but solving this particular problem will actually make you an instant millionaire, because there's a place called the Clay Institute, and the Clay Institute is actually offered. The Clay Institute is offered a prize of $1 million to anybody who can solve the P versus NP problem. And I should say it won't make you a instant millionaire, but the reason for that is that the institute will have to verify that whatever solution you came up with is correct, and that might take some time. But you do have the potential, if you pay attention to this set of videos, for potentially figuring out how to make $1 million. So I think that's some interesting motivation beyond just the intellectual challenge of looking at this particular problem. Okay? Now, this particular problem, ultimately, the P versus NP problem, concerns the amount of time it takes for you, or for a computer rather, to solve a particular set of problems. Now, in some cases, there are problems that we know how to solve quickly on a computer. And this shouldn't be a surprise to you because, after all, computers are indeed very, very fast. But there are other problems that we don't really know how to solve quickly on a computer. In fact, they can take a long time. And what's interesting is that we don't really understand from a fundamental mathematical perspective why it is that these problems seem to take a long time. And that's really the heart of what the P versus NP problem looks at, is why is it that certain problems take a long time on a computer. Okay? Now, this problem of the P versus NP, this actually is a problem that belongs to a branch of computer science. In fact, it's a branch of computer science that intersects with mathematics, known as theoretical computer science. Okay? And within theoretical computer science, there's actually a sub-branch of theoretical computer science known as computational complexity theory, often just abbreviated as complexity theory. And complexity theory basically asks, as the name might imply, how, let me actually get that right, complexity theory, and actually, let me clarify, this is not just complexity, it's actually sometimes known as computational complexity theory. Okay, computational complexity theory, as its name might imply, is concerned fundamentally with how complex certain problems are from a computational perspective. In other words, really, how hard is that problem to solve? How much is required in terms of underlying computational resources to solve that problem? Okay, and by computational resources, I mean things like, how much time is required on a computer to solve the problem, how much space is required, and space typically refers to things like the computer's memory or its hard drive space, for example, the RAM on a computer, and that sort of thing. And there are other interesting computational resources as well that you might be concerned with, such as, let's say, the amount of power consumed by the computer. For example, if you're dealing with a mobile device, that might be particularly interesting because a mobile device might be limited in battery power. Okay, but typically people focus on time as the major resource, and there are branches of complexity theory. People look at space as well, but for the most part, people are mostly concerned with the amount of time that's required to solve a particular problem, assuming a particular computational model. Okay, now if you think about it, theoretical computer science really asks some of the most basic, basic and fundamental questions that you could possibly be interested in when it comes to computers. And these are questions around the lines of how hard is it to solve certain problems on a computer. If you have these things that are called computers, they're wonderful, they have these great properties, and you want to know, to start with, maybe what you can solve, and then in particular, what can you solve in a practical amount of time on that computer. So let's actually start off and dive right in. And I want to give and start off by giving maybe a motivating example. Imagine I asked you something very simple. I said, here are two numbers, 143 and I don't know, 357. And I said, okay, what's the sum of these two numbers? Okay. Now, if I gave you this problem, let's say, imagine I gave this problem to a small child, one who maybe just learned how to add numbers. What they might do is they might, for example, try to count, starting at 143 and count 357 more. And they could probably do that by some type of a number line. So they might draw a number line and start that number line at 357, and then maybe count upward. Or if they were not clever, they might start the number line at 143 and try to count an additional 357, and so on and so forth. And they would eventually arrive at an answer by taking that particular procedure. Now, hopefully you know, if you've taken math beyond the elementary school level, that there are much faster algorithms for solving this particular problem. And actually, maybe I should segue really briefly. I'm going to be using the term algorithm quite frequently during the course of this video series. So let me actually specify what an algorithm is. So basically, in my mind, we think of an algorithm as a method. Okay, it's an algorithm is a method for solving a problem. Okay, it's a method for solving a problem that produces a correct answer always. So it's a method for solving a problem, and it has to be a correct method. In other words, it always produces the correct answer. And there are slight variations on theme here, but this is really what we're going to mean. This is what we're going to mean when we talk about an algorithm in our context. Okay, I do want to point out, maybe as a bit of history lesson, that the term algorithm itself actually comes from the name of a very famous Persian mathematician. His name was Muhammad ibn Musa al-Khwarizmi. And aside from being the eponym of the term algorithm, Muhammad ibn Musa al-Khwarizmi also happens to be the person who is credited with establishing the field of algebra as a proper mathematical discipline. In fact, the term algebra is derived from a Arabic word, which is al-jabr, which I think means to restore. So al-Khwarizmi is made a number of impacts in the fields of mathematics, but his name, al-Khwarizmi, is how the term algorithm was derived. Okay? So now let me actually get back to our example that we started talking about earlier. Imagine you got two numbers and you want to add them, and we said there's a slow method to add them, but there are much faster methods. In fact, one of the fastest methods you can use to add up two numbers is the classical grade school algorithm, and that basically involves starting really from column by column, and you would, I guess, maybe start at the right if you're looking at the screen, and you would add up each column, and if there's a carry, you would carry that number over, and you would arrive at an ultimate answer. And in this particular case, you would carry whenever the number is 10 or greater for a particular column, and if you proceeded in this way from right to left, or from left to right, depending on how you're looking at the screen, you would ultimately arrive at an answer of 500. Okay? And it is worth